Hi students. So we have already discussed about the difference between classical computation and quantum computation. So after that, the next topic that we have in our syllabus is linear algebra for quantum computation. Now before understanding linear algebra or before understanding linear algebra for quantum computation, let us first briefly revise some concept that you have learned while studying vector analysis. So, I think you all know a vector is a quantity which has a proper direction and a magnitude. So, all the vectors are associated with some kind of direction and some kind of magnitude. So, now let us consider a vector, say A vector. So, if we write the x component, y component and z component of A vector, so let A vector is A1 I cap, where I is the unit vector along x axis, plus A2 j cap plus A3 k cap, where j cap and k cap are unit vectors along y axis and z axis respectively. And also consider another vector, say B vector. So, B vector is represented by, say, B1 I cap, then B2 j cap plus B3 k cap. So, here B1, B2 and B3 are the components along x direction, y direction and z direction respectively. So, now actually linear algebra, it deals with the study of vectors and some linear operations done on vectors. So, how vectors are represented in case of linear algebra? In linear algebra, remember I told you in my very first class that in your mathematics syllabus you are dealing with matrix, right? So, in the study of this third unit also, the knowledge of that matrix will be very important for you. So, linear algebra is that part of mathematics which deals with the analysis of vector with the help of matrix. So, in case of linear algebra, the vectors are represented in terms of some column matrices. So, if A vector is equal to A1 I cap plus A2 j cap plus A3 k cap, in the language of linear algebra, this vector will be represented as a column matrix having three components A1, A2 and A3. Now see, this column vector can also be written as A1 into 1 0 0. You already know about matrix multiplication. So, A1, if A1 is a scalar, A1 multiplied by 1 0 0 represents A1 0 0. Next, we will write A2 into 0 1 0 plus A3 into 0 0 1. If we do this addition, then it will generate this column matrix A1, A2, A3, which will represent the vector A. Now you see here, what did we write? A vector is A1 I cap plus A2 j cap plus A3 k cap. And what did we get here? A vector is A1 into 1 0 0 column matrix plus A2 into 0 1 0 column matrix plus A3 into 0 0 1. So, just compare these two expressions for A vector. Here we are multiplying I cap with A1 and here we are multiplying 1 0 0 with A1. So, that means this I cap, this unit vector along x axis, is represented by this column matrix 1 0 0. I cap is represented by the column matrix 1 0 0. And similarly, j cap is represented, the unit vector along y axis is represented by 0, 1, 0, and unit vector along z axis, that is k cap, it is represented by 0, 0, 1. So, like I cap, j cap and k cap, in the language of vector analysis, we call them unit vectors. In the language of linear algebra, these column matrices 1, 0, 0, 0, 1, 0 and 0, 0, 1 are known as the three basis states representing a three-dimensional state vector. So, these column matrix having three components, these are called as state vectors. It represents the state of a system, the position of a system. Or here this a1 I cap plus a2 j cap plus a3 k cap, they generally they are related with the position vector. But similarly, any vector we can have, say force or momentum, any vector, they can also have x component, y component, z component. So, r vector, the position vector r vector. So, position vector, what it is? It is xi cap plus yj cap plus zk cap. So, in the language of linear algebra, how will we represent r vector? It will be represented as x, y, z. So, by a column matrix, the first component represents x component, second one represents y component, and the third element represents z component. So, for representing a three-dimensional vector, we will have a column matrix having three elements. So, in our day-to-day life, every time we encounter with three-dimensional vector, because we are living in a three-dimensional space. We are living in a three-dimensional space. Here all the vectors are represented by a column matrix having three elements. But just imagine, in a quantum system, a state psi, it can have various components. I told you, if you open your notes on quantum mechanics, you will see there at one point I described this eigenstate psi. It can be constructed using various component states. So, psi can be written as summation over small n's, where small n can take any integer values, Cn psi n, where psi n represents the component states and Cn can be any constants. So, psi can be something like C1 psi 1 plus C2 psi 2 plus C3 psi 3 and so on. So, a quantum state can be represented by a combination of n number of components. Here, in case of three-dimensional vector, we have only three components, three linearly independent components. This I, x-axis, y-axis and z-axis, they are mutually perpendicular to each other. That means they are linearly independent. X component does not depend on y component value, y component value does not depend on z component value, they are linearly independent. But a quantum system can be expressed as n number of linearly independent components, where this n can take any value. So, in case of a quantum system, instead of having only three elements, we can have n number of elements, where this n can have any value. So, basically quantum state vectors are n-dimensional vectors. Wherever we will have a column matrix, this column matrix, in the language of linear algebra, all the column matrix corresponds to some kind of vector. They have some directional property. Each of the component represents one linearly independent direction. So, in quantum system, we can have n number of linearly independent components. So, they will correspond to a case of n-dimensional, a vector in n dimension. So, they correspond to n-dimensional system, n-dimensional vector system. So, this thing only we have briefly written in the notes. Now, go to your notes. If you go to your notes, Just read it, just see. Linear algebra, what we told, is the study of vector spaces and linear operations on those vector spaces. A vector in linear algebra is defined by a column matrix. The thing we have said just now, a position vector r xi cap plus yj cap plus zk cap is represented by xyz, and in quantum system where we have n dimensional systems, so similarly by increasing the number of elements in column matrix, a state vector with larger dimension, which happens in the case of quantum system, can also be represented in linear algebra in terms of a column matrix having n number of elements. And also remember one additional thing, each element here in quantum system can be complex, can be represented by a complex number also. So here Zi represents the ith complex number, ith complex component of the state vector. And these vectors, now about operations, linear operations. So these vectors obeys the law of vector addition. What is the law of vector addition? So if we add a vector and b vector, what will we have? What will be the result? What will be a vector plus b vector? So a vector plus b vector will be, you already know this, I think, vector addition you all know. A vector plus b vector will be a1 plus b1 I cap plus a2 plus b2 j cap, a2 plus b2 j cap plus a3 plus b3 k cap. So the same thing has been represented here. While we add two column matrix corresponding to two state vectors, each component, the addition will occur component by component. Each components will be added, and that will correspond to the component of the summation, components of the result. And when a scalar quantity is multiplied with the state vector, with the column matrix. So what happens when we multiply a scalar quantity with a column matrix? Each element of the matrix will be multiplied by the scalar quantity. You are already reading about matrix operations in mathematics. So I think you already know, when we multiply a scalar with a matrix, each and every element of the matrix will be multiplied by the scalar. So this is the result. The same thing happens when we multiply a scalar with this vector. So a vector is a1 I cap plus a2 j cap plus a3 k cap. If we multiply a scalar quantity n, or say any scalar quantity, say c, okay, c a vector will be c a1 I cap plus c a2 j cap plus c a3 k cap. So each and every component will be multiplied by the scalar quantity. So that thing has been written here. These are the two basic laws obeyed by linear algebra, which constitutes the linear algebra. So this is linear algebra for vector analysis. Next we will discuss linear algebra for quantum computation. We have not gone to that part yet. But before going to the part, we will briefly discuss about Dirac's Bray and Kate notation in our next video.